and let me get started again. Okay. Yeah, let me just get started again. Hi, everyone. I'm Mike, and I'm a PhD student from Princeton University, and I'm here to present our precision paper on ranking formal specifications using LLMs. And this is a joint effort with Zhendong from National University of Singapore, Ankush Desai, and my advisor, Aarti Gupta. And as many of us are familiar with, reasoning about correctness involves checking an implementation against formal specifications, whereas these formal specifications serve as the heart of formal reasoning. And this technique is widely adopted in various verification tasks. And to our experience in this process, articulating formal specifications precisely is a huge burden to the developers. And this is especially difficult and time-consuming in the domain of distributed systems, where developers have to think about the specifications with presence of asynchronous communications and potential failures. For instance, consider a simple client-server database protocol, and with these four types of message exchanges. And under this model, the developers need to think of specifications that may involve these messages, and each pair of them can capture certain correctness conditions, such as atomicity and liveness. And this soon will be very burdensome and intractable with more types of messages in the protocol. And to alleviate this burden, several prior studies have been conducted to develop automated procedures to mine specifications from execution traces. For example, DICOM mines program invariants using program traces. And these techniques produce likely invariants that hold across all the given traces, which may contain correctness conditions that the developers are looking for. Though these data-driven techniques have very good scalability, they often produce too many likely invariants, which can overwhelm the developers. For instance, for an implementation of the Raft consensus protocol, a previous work dinf, which learns likely invariant from state traces of system, can produce 1 million of them. And this is without proper user guidance. And a more recent work, inferred, which we developed at AWS, reduced this number to around 100 by using a more exhaustive pruning step, leveraging a model checker. However, this 100 can be still too many for developers to look at. And this brings a new challenge to the developers using these techniques, which is identifying meaningful specifications from a large and noisy set. So to address this challenge of identifying meaningful specifications after mining, we considered some potential approaches. First, which is the simplest approach. Let's just hire someone to do it. Let them pick the specification for us, or some expert. Well, an expert can be very good at picking or spotting these meaningful specifications. This cannot be applied at scale and let them to read maybe 1,000 lines of formulas. And next, what about deductive verifiers, such as IV or Z3? Well, these verifiers usually would have to prove the inductiveness of these specifications. But usually some meaningful specifications or interesting specifications are not inductive by themselves. And therefore, these approaches can fail to identify certain meaningful specifications. Moreover, this approach is not scalable due to the inherited performance and the theoretical limitations of the verifiers when handling more complex program models. And what about model checking? Well, model checking can preserve the meaningful specifications with slightly better scalability for more complex systems. However, they cannot exclude the ones that are trivially true and that will make the set noisy. And this is to our experience developing that inferred framework. Therefore, we asked, why not to try something like an LLM to mimic the thought process of experts or developers when they are picking these specifications? But whether these LLMs can find meaningful specs and whether they can be applied at scale it remains unknown. And we aim to investigate these two aspects in this project. So before jumping into how we use LLMs, let me first introduce some background on the program models we are using and the form of specifications we are working with. Well, our examples are all focusing on these distributed systems and protocols. This technique itself can be similarly applied to other domains, such as program verification. So we consider distributed protocols modeled in P language, which is a state machine-based programming language. And in P, each component in the system, such as client, server, and database, is modeled as state machines with local stores and states shown in the listing on the right. You don't need to read all of the details in this listing, but it shows the overall structure of a P program with machine definitions, message exchanges, and state transitions. For specifications, we focus on first-order logic formulas over exchanged messages. For instance, this formula says that for all write requests and response, if their request ID is the same, then the request must happen before the response. And this preceding sign denotes this classical happen before relation. We also allow existential quantifications over events, such as one shown here, which says that for all write response, there exists a request happened before with the same request ID. So, given a specification in this form, how do we, as a human developer, assess the quality of it? So we thought we need to think through this ourselves first. Well, first we ask whether it is a correct specification. And if it's a correct, then we look into whether it's encoding or capturing certain interesting or critical behaviors of the protocol or the system. And then we ask whether it serves as a good separator to separate the good behaviors from bad behaviors. And finally, we consider the clients, like whether the violation of such a specification will result in some immediately observable failure to the clients. And the answer to these questions are all yes. We'll put these specifications into a golden set. And if it's even not a correct specification, we will just immediately throw it away. And if it's no or partially yes for the rest of the question, it's the case that we consider it as some property with a minor significance. So following this thought process, we propose a four-metric rating framework that assigns ratings to each specification formula. And our four metrics include generalizability, which measures whether the specification generalizes to unseen execution since they are mined on some finite set of traces. And criticality evaluates the severity when the specification is violated. For instance, whether this violation can cause some cascading effects to the system, finally leading to some service outage. And the distinguishability measures how well does a specification serve as a separator between good and bad behaviors. And finally, visibility measures how directly a violation is visible to the end users. So let's look at some examples. The formula shown in the middle states that the write responses to the same request should carry the same status code. Well, this is obviously generalizable to all correct executions, since we desire such consistent model. And it is also critical because because the inconsistent commits can in consequence lead to inconsistent reads, and that is something we want to prevent. And it also distinguishes executions that can lead to inconsistent commits, and it's visible to the user, since on the right, the figure on the right, you see that the write response immediately sends to the client, and they can tell the discrepancy. And for another example, this specification over commit responses asserts that there is a unique commit response from the database. Well, it is not quite generalizable and critical, since the protocol may allow the database to send multiple commit responses when, for example, there is a network partition. It retries these commit response when it detects such outage in network. However, it does distinguish correct from incorrect behaviors, because any inconsistency can be excluded by this very strong uniqueness of commit response property. It is also highly visible because, as you see on the right-hand side, the commit response will be immediately directed to the client, and in return, they will see the duplicated commit responses. So formulating this rating framework, we leverage LLM as a judge to evaluate the specification formulas. It takes in the description and the criteria of the rating framework, and the specification formula, and the summary of the P model, and a few examples of assigning ratings to the formula. And the LLM is prompted to produce 4 confidence scores for the metrics, and an overall score is computed as follows, where the lambdas are hyperparameters to control the significance of each metric. And finally, we rank the specifications based on the overall score from highest to lowest. So we did some preliminary experiments to evaluate the effectiveness of this workflow. And in particular, we selected 14 protocols, where 11 are from established works, such as Paxos, Raft, chain replication, all these well-known protocols, and 3 from our proprietary services, which worth to note that the LLM must have never seen their implementation and specifications. And the input specifications to rank are produced by our p-infer framework, and we crafted a set of goal specifications, which we hope the LLMs can rank them at the top. And for the established protocols, these are from original papers of those works. And for the proprietary protocols, these are written by our service teams. And our evaluation criteria is to take the top K ranked specifications and check how many in the goals are being covered by these top K. And for the experiments, these preliminary experiments, I hard-coded these hyperparameters to give it more significance to the generalizability and criticality score, because empirically we found that this represents some kind of quality term of the specification. And this table shows the results of our ranking workflow, where the top half and the bottom half show the data for established and proprietary protocols respectively. The number of input specifications in each benchmark is shown in the parentheses. And each row or each column after it shows statistics when taking top K ranked specifications, where each colored cell shows the number of goals being covered within top K over the total number of goals. And this is passed at 1. For instance, this cell says that 2 out of 2 goals are covered within top 10 ranked specifications. And we prefer the green colors in this table. Some highlights. So all the specifications are covered within top 50, and many are covered within top 10. And moreover, the cost is not negligible if you see the last column showing the cost in money, in dollars. And we compared it to a baseline ranking approach, which ranks formulas by term frequency, and we take the atomic predicates in these formulas as terms, and we rank them from lowest to highest. And the intuition behind is that rarely learned predicates might worth more attention to the developers to look at, whereas a frequently learned predicates or mined predicates may be just truly true. And in this figure, the x-axis shows the value for k in top k, and the y-axis shows the number of benchmarks with all the goal specification being covered. And we can see that our proposed workflow achieves full coverage as shown in the previous slides at k equals to 50. While the baseline approach reaches a bottleneck, seems around this k equals to 60. And we wanted to investigate where does the baseline get stuck. Therefore, we plotted out the distribution of the goal specifications under each of their ranking under each approach. And we've discovered that the baseline struggled with the 2 benchmarks that has the most and the second most number of input specifications. And this kind of indicates that the predicate frequency heuristic can get inaccurate when the input set gets further noisy. So in summary, hopefully, I convinced you that with some proper user guidance and domain knowledge of what does this quality of specification means, LLMs can identify meaningful specifications and can potentially scale to large scale, like industrial applications with very low cost. And one bonus point we can earn here is that we are not asking the LLMs to generate the specifications on their own, but rather picking from a set mined by some upstream mining procedure. And therefore, the soundness of that mining procedure can be guaranteed by this workflow. So how can this whole thing be important? Let me flash through this page. So it helps identify specification from a large set, and it can also help the LLMs, in fact, especially for the auto-formalization procedure, where a lot of, like in test time scaling, you can generate a lot of specific formulas for a certain program you want to verify with LLM-generated code. And it can be potentially extended to a broader verification framework by identifying specifications and mutually inductive invariants to finish the proof. And how can we make it better? Well, there are many ways to make it better. Always can make it better. But I want to point out that we could integrate this into a verification workflow with P-Verifier, which is a project we are currently actively working on, after identifying important specifications. And here are some resources to give you further background and information about P and its ecosystem and our workflow. And thanks for listening. And I'm happy to take questions.
thanks. Let's thank the speaker here. We can probably have one quick question while the next speaker is setting up the computer. Anastasia? For questions.
I missed the first few slides, so apologies if I might be repeating stuff. Yeah. But I was wondering if you guys had looked into how you might get input from the domain experts in order to construct the specifications.
So actually, the input of this workflow takes specifications that are given by some mining procedures that automatically discovers these likely specifications. Like there's techniques like DICOM, which they mine specifications from execution traces. Basically, it will give you a set of propositional formulas over program variables that hold across all the executions. And we take those as input. And it can generate a lot of them because it's a kind of a grammar-based enumeration, a grammar-based synthesis of these formulas. We can generate a lot of them, and we want to identify critical properties within this noisy set.
Oh, yep, got it. Okay, thanks so much.
Yeah, no problem.
All right, let's thank Mike again.